And I want to talk about inductive limit of filtered infinity category. And the main applications is I want to explain the three theorems. And the first one is the following things. Suppose we have this symplectic manifold, which is compact or convex at infinity, and we take a finite set of Lagrangian submanifold, and we don't assume. So it's important that we don't assume the transversality among the Lagrangian submanifold. And the first theorem says the following things. So without assuming this transversality, we can still construct this filtered infinity category over lambda 0, Novikov ring, which I will explain what it is. So that its object is Lagrangian submanifold and bounding cochain. And it's a so-called completed homology of the morphism spaces. It's some kind of inductive limit of Fourier homology, which I will soon explain. And this is well defined up to weak equivalence. So what this means? So we don't assume any kind of transversality. So we take some Hamiltonian isotopy, so that this Lagrangian submanifold is transversal to the second one. And this P1 and P2 are different. And then we take this Lagrangian Floer theory. And this morphism space is some kind of inductive limit of this perturbed things. And this isomorphism is something called almost isomorphic, which I will explain soon. And this homology is something like a completed versions. I will soon explain. Okay, so now I need to remind you the following things. We first consider this Novikov ring. That is a kind of formal power series ring. Of this AI is something like a real number, and this T times lambda I, and lambda I is non-negative real numbers, which goes to plus infinity. This is Novikov ring. And if we allow this lambda I to be a negative number, that's called Novikov field. And I need to remind you one thing. If you consider Floer homology between two Lagrangian submanifolds over Novikov fields, then this Floer homology is invariant under Hamiltonian isotopy. So in these cases, we can make our Lagrangian submanifold to be transversal to each other by Hamiltonian isotopy, so that we can reduce this theorem to the case that all these Lagrangian submanifolds are transversal. In that case, this is already established many years ago. But here, today, I insist to study over Novikov ring. And over Novikov ring, Floer homology is not invariant by Hamiltonian isotopy. And there are a lot of interesting torsion structures that are kind of our main interest. So that, in that sense, this theorem is new. Now, I also remark that we can just generalize the following things. Suppose we have a sequence of Hamiltonian isotopies, which so that it's a difference of this is Hofa norm. It is a kind. The sum is finite. It means that it is a kind of goes quickly to 0, and and then we consider we can make this Lagrangian submanifold to be transversals, and we consider this sequence to be so we just perturb this, and we can still take the limit. It means that you have some kind of Lagrangian, set of Lagrangian submanifold, which is in a sense a Cauchy sequence with respect to this Hofa distance, and then we can still construct this infinity category in this limit. So that's something I want to do today. So this is the first applications. And the next application is something I want to call it C0 most homotopy. So we take a set of continuous functions. So we take finite set of continuous functions on a smooth manifold. Then we can still associate some infinity category. And this one has the following property. So that this infinity category has an object of this continuous functions. And this filtered infinity category depends in a C0 norm on this finitely many continuous functions. Of course, we need to say what do I mean by depends continuously. And I will introduce some topology on the space of filtered infinity category soon. And in that sense, this depends continuously on the C0 norm of this finitely many continuous functions. And also this is well defined up to some notion of weak dependence. And in the case when these all functions are smooth and the difference are bottommost, then there is something called the Morse homotopy, which I studied in the 90s. And in the case of this bottommost functions, then this one is Morse homotopy, which introduced in the 90s. So this kind of system limit is related to something called a persistent homology. And I think basically the fact that this persistent homology depends continuously on a Caesar norm of the function is known in a study of this persistent homology. But we can include this product structure, that are infinity structures. So that is the second theorem. So I want to mention third main applications of this construction. That is the composition of Lagrangian correspondence. So maybe I say that you have a kind of, you have two symplectic manifolds. And then we have this Lagrangian correspondence. So that is a Lagrangian submanifold of product. So this is I'm sorry. According to Weinstein, so we want to regard this kind of Lagrangian correspondence as a morphism of the category of symplectic manifold. And then the composition is something like this. You have a kind of L12 contained in minus x1. Minus x1 means just to take a minus of symplectic form. And if L12 is the Lagrangian submanifold of x1 cross x2, and the L23 is minus x2 cross x3, then the correspondence proposed by composition of two morphisms proposed by Weinstein is L12 fiber product over x2 of L23. And then this goes to minus x1 cross x3. And this is a kind of product composition. But the issue is, of course, so in a case if this fiber product is generic, it means that it is transversal. Then one can show that this fiber product is immerse Lagrangian submanifold of x1 cross x3. And this is what Weinstein proposed. But in general, this fiber product is not transversal. So in a sense, Weinstein category is not a category, but it's a kind of topological category. But the third theorem claims that we can actually compose without assuming transversality. So the statement is the following things. And to make this story to be kind of work with Floer homology, we need to add so-called bounding cochain, and we work in the following things. So suppose we have this finitely many Lagrangian submanifolds of this product of xi cross xj, or 1, 2, 2, 3, 1, 3. And we cook up this filtered infinity category on this associated to this 3 Lagrangian submanifold. So you have this category associated to this Lij. And then we can enhance this L13 to include a bit more object, and we can construct this composition functor. So it's a kind of direct product of this L12 and L23 unto L13 plus. So this is something like gives this composition of Lagrangian correspondence. And what it is, so this object, so this OB means that object of this L13 plus is object between original L13 plus this direct product. This means that something obtained by composition is also an object. And this composition functor, as far as object concerned, it just correspond to this, that you have a pair of elements here. You can just take the element here. And in a case everything is transversal, then this is constructed by Mao, where you have Woodward. In a case this every Lagrangian submanifold involved is embedded and monotone. And I generalized it to 2017. In a case, everything is transversal, but not necessarily, but not necessarily monotone or embedded. But we further generalize so that we don't assume any transversality. And this third thing is just, this is something like a reasonable thing. So this x12 is a diagonal. So if you consider this, oh, I'm sorry, this is S23. So you can just take this Floer homology of, this is Floer homology of L12 and L23, and diagonal of x2 with this L13. It means, you know, these two are somehow this Lagrangian submanifold of x1 cross minus x1 cross x2 cross minus x2 cross x3. So in this symplectic manifold, we take this Floer homology, and that is this morphism in this composition spaces. So this is a kind of composition of Lagrangian correspondence without assuming any transversality. Okay, so these three applications I want to of the construction I want to explain. Okay, so now I want to explain something. So some notions I want to introduce. So the first thing I want to introduce is this topology on the set of filtered infinity categories. But before I introduce the topology on the set of filtered infinity categories, I want to introduce a topology on an object of the set of on a filtered infinity category. So we consider this filtered infinity category, and which is over Novikov ring. So this is something like and lambda I is non-negative. And so I want to define this topology between two objects. That's called, I want to call Hofa distance. That's the following things. So we consider it's extension field to Novikov field. So we just take, so this is a space of morphism between two objects. That is a chain complex of over this Novikov ring, and I want to take this extension of the field. So you have this chain complex over Novikov field. So this is a kind of infinity category over lambda. And you have two objects. The Hofa distance is defined the following way. So you have this A, you have this B. And the Hofa distance is smaller than epsilon. We have some morphism T from A to B, which is defined over Novikov field. And you have a morphism in opposite directions. And this is actually a honest map. It means that it is a cycle. And then if you compose, so if you compose T and T prime, you get a morphism from A to itself. And this one is homotopic. So this one is identity morphism. So if you go back, you take T and T prime and come back, it is homotopic to identity. And if you compose T prime and T, also it is homotopic to identity. So this means that A and B is something like equivalent in this infinity category. And so that's first thing. And then we want to require that, you know, this T prime, S prime is not contained in this original infinity category defined over lambda 0, but only after this inverting T. However, so you have this kind of negative energy, but this energy is almost non-negative. It means that you just take tiny epsilon, tiny epsilon 2, and tiny epsilon, then it is contained in this original morphism space over lambda 0. And this epsilon is this one, and epsilon 1 plus epsilon 2 is epsilon. So this is what I want to call Hofa distance. And so this is something like a metric on a space of on a space of object of filtered infinity category. And there is one theorem that is the reason why I call it Hofa distance. So suppose you have this Hamiltonian isotopy from a symplectic manifold to itself. And you consider two objects. One is Lagrangian submanifold L, and then you have this L, and you take this phi of L. And the theorem says that this Hofa distance between two objects is just estimated by Hofa distance of this phi between phi and identity. So I mean, Hofa defined this metric on a space of Hamiltonian isotopy, and so this Hofa's this action on a Hamiltonian isotopy on a space of morphism on Lagrangian submanifold is just continuous with this Hofa distance. And this is basically proved in our paper with Ota Ono in 2009. And but kind of we can just take that proof and using this language, and then we can prove these theorems. So this is why I want to call it Hamiltonian isotopy. So Hofa distance. So this is a kind of metric on this space of object of infinity category. So now I want to.
Can I ask a question?
Yes, please.
Can you go back to the previous slide?
Yes.
So it's not completely clear to me, but it looks like an interleaving distance. Is it the case?
This is actually a distance. We can prove triangle
No, not understand, but is it a kind of interleaving distance, like for persistent modules?
Yeah, in some cases it can be infinity. But including infinity, yeah, it's a metric.
Go ahead.
Yeah. So the next definition is a metric on a space of filtered infinity categories. I want to call it Gromov-Hausdorff distance. So suppose we have these two filtered infinity category with unit, and its Gromov-Hausdorff distance is smaller than epsilon. If there is, so you have this C1, I have this C2, and they contain in the third filtered infinity category. And this object of the C is just this union of object of these two of things. And there is a homotopic equivalence to full subcategories. So they are embedded in the C. And if you consider this object set, then you take this usual Hausdorff distance with respect to this Hofa distance, which I have just included, then it's smaller than epsilon. And we assume there's some gap to this combination. That's technical. I don't want to explain it. So if you know that this definition of Gromov-Hausdorff distance in the case of usual metric spaces, then this is exactly the Gromov's definition of Gromov-Hausdorff distance. But we just include this kind of infinite structure is preserved. So this is a definition of Gromov-Hausdorff distance, and we can also prove this triangle inequality. So so I just mentioned that continuity of some filtered infinity categories, and it is continuous with respect to distance. So I just to explain two examples. One is that you have a filtered infinity, one filtered infinity category with a strict unit, and we take some two system of the object, Ci and C prime I, and we take full subcategory so that this C and C prime are the set of objects. And then we assume that the Hofa distance between Ci and Ci prime is smaller than epsilon. Then the Gromov-Hausdorff distance between these two full subcategory is smaller than epsilon. This is just like a tautology. And the second example seems to be more related. So we have these two M smooth functions, and so that its difference are bottommost. Then we consider this most homotopy filtered infinity category by this F1 to Fm and G1 to Gm. And then this Gromov-Hausdorff distance I just introduced is smaller than the C0, supremum of C0 norm and Fi and Gi. This is some kind of so I just explained this Lagrangian version of this statement. And then there is a kind of Moss theory version of this theorem, and that implies this estimate. So now this is the second example. And the theorem, so the kind of main, this is not algebraic theorem, but the main algebraic statement, main algebraic inputs the following things. If we consider a sequence of Cauchy sequence with respect to this Gromov-Hausdorff distance of filtered infinity category, and then we can construct the limit. So in a sense, this is a complete, so this Gromov-Hausdorff distance is complete with respect to, I don't know, the set of infinity category is complete with respect to this Gromov-Hausdorff distance. But I don't claim it in that sense, because original thing should be to be gapped. And the limit is not gapped. So gapped means the following things. Gapped means that you have this operations, infinity operations, and this is something like the sum. So MKI is something like R linear. So our filtered infinity structures has some this kind of form, and this lambda I should be contained in some G, and G is some discrete set of non-negative real number. So this is called a gapped conditions. This lambda I is basically the set of holomorphic disks. In the case of Lagrangian submanifold, this lambda I, the set of holomorphic disks, which I'm sorry, the symplectic area of the set of holomorphic disks. And that is the discrete set because of the Gromov compactness. So that is gapped conditions. But and if you go to the infinity, so you have just two Lagrangian submanifold, which are very wildly intersected. And you cannot apply Gromov compactness in this kind of situation. The set of holomorphic disk is not discrete. So if you go to the limit, you cannot expect gappedness. But the situation is that you have a constant sequence of gapped infinity categories. Then the limit still exists, but it's not gapped. So this is a theorem. I want to. So this is the first part of this explanation of the theorems. And the next thing is that I want to explain weak equivalence. So I say that I say that there exists some infinity categories, but it is not completely well defined. It's got well defined with respect to weak equivalence. And the definition of weak equivalence is that if the Gromov has no distance of these two categories is 0, then it is weakly equivalent. I think Gromov proves that if two metric spaces and the Gromov factors distance is 0, then two metric spaces, maybe something like completeness or something, then these two metric spaces are isometric. But that's a bit nasty statement to prove in our situations. So we cannot prove that the Gromov factor distance is 0 means that it is equivalent. But so I introduced this weak equivalence. And then I say that these two metric is kind of has this triangle equality. This means that weak equivalence and equivalence relations. So I want to explain this two more notions which I explained: complete homology and almost isometric. So suppose we consider a sequence of non-negative integer or infinity, and then it is a non-increasing sequence. Then we construct this lambda 0 module. So you take this lambda 0 divided by t to the power ai of the lambda I. Then you take this direct sum and complete it. It is this t to the power ai. So it's something like something like this. So you have a0 is go to infinity, a1 go to infinity, and this is stop a2 and a3. A4. So something like this. And what we proved in this 2009 with Ota Ono is that if this two Lagrangian submanifold are transversal or clean, then the Floer homology is this form. So you have this kind of sequence, non-increasing sequence, so that this you have this kind of structure. And this one is 0, except finitely many I. And moreover, we prove the following things. Suppose you have these two Lagrangian submanifold L1 and 2, which are transversal, and you have two Hamiltonian isotopy, so that after kind of moving L1 and L2, this will get again transversal. And suppose that the Floer homology is lambda 0 a vector, and after this taking this Hamiltonian isotopy, you take this a vector prime, and then the difference of this exponent is smaller than, not greater than Hofa distance of phi and phi2. This is something we proved in our book. Okay, now so if you consider this pair of Lagrangian submanifold, which is not necessarily transversal, then we take the sequence of phi n, so that Hofa distance goes to 0. But then we prove this. We assume that phi n of L1 is transversal to L2. We can certainly take that sequence of Hamiltonian isotopy. Then we take this Floer homology between phi n L1 and L2 is in this form, and then this theorem says that if you take this sequence of ain when n go to infinity, and this estimate shows that this is a Cauchy sequence, so we can take its limit. This is ai infinity, and our definition of Floer homology in a non-transversal case is just to take this lambda 0 infinity. And I remind you that for n finite, this n is a kind of 0 except finitely many I. But if you go to the limit, you have this. This is not finitely generated. This means that you have not infinitely many I and infinity. It's something like this. There are you can. This is not finitely generated. And what I say the following thing. So we consider this limit, And this is a limit in a sense just I have defined. And then this morphism space of this limit filtered infinity category is something called a almost isomorphic. And this guy is something called a completed homology. So this main theorem 1 implies that if you take this kind of thing, then if you just take this almost isomorphic, then all this multiplicative kind of infinity structure survives in this limit. So I want to explain these two notions, almost isomorphic and completed homology. It's the following things. So suppose we have this filtered lambda 0 module. Then we take this something called a spectral closure. It's something like this. You take this element of x, so that you take this t epsilon of x and w, then this is closure. So it's that most example is that w equal lambda prime. This means that and Li is all positive. You take the spectral closure, then this is lambda 0. The 0 is allowed. So it is non-trivial operation, but in a finite generated case, this is trivial operation, but in a not finitely generated case, you have non-trivial things. And you have a cochain complex of FT lambda 0 module. Then the completed homology is just to take this kernel and the image, but they take this closure. So that is completed homology. And almost isomorphic means the following things. So suppose that we have this lambda 0 module, which is generated by an element of energy 0. And you take all this lambda in a positive number, and we define this so-called spectral dimension in the following things. We take some finite generated submodule of this, and then this we take the smallest number of generator of this W, and this dimension is just a maximal number of the smallest number of generators. And the good example in this case, you have this kind of situations. You have some infinity, and then you stop here. Then we consider this lambda. Then we count all this component, something like lambda 0 divided by t ai lambda 0, which is above this lambda. Then the sum of that kind of thing is this spectral dimensions. So this is a kind of non-increasing, non-decreasing functions, and this is a kind of when lambda go to 0, this typically diverges to infinity, and so this is a kind of spectral dimensions. And in the case of this typical kind of, in the case of this finitely generated, the Floer homology is always in this form. So in that case, this spectral dimension determines this isomorphism type. But in a nasty case of infinity generated case, this may not determine. And I just defined this almost isomorphic. This spectral dimension coincides. After the discrete set when they are discontinuous. So this is an integer valued function. So it kind of jumps. And on a place when it jumps, so you have kind of some functions which may jump, and on other place it jumps. You may take this guy or this guy, and that may not be the same, but almost everywhere it coincides. So this is almost isomorphic. Okay, I just want to mention one conjecture that if this Lagrangian summary for the all real analytic, then this completed Floer homology is finitely generated, and this infinity category is actually gapped, but I cannot prove it. So let me consider the case of this. So the case of most homotopy cases. Suppose we have these two Lagrangian summary for which are transversal. Then we defined in this Floer homology filtration of Floer homology, so that this geometric generator have energy 0. This is a kind of convention, but that's our convention. But if you consider this most functions, and the convention, the usual convention of the most homology is that this geometric generator has energy value of most functions at p. So that's two different conventions, and there are reasons that we take these two conventions. For example, homological algebra of infinity category works better than if these two generators has a kind of energy 0. So, but then, of course, this convention has a very good reason, because this structure is very important. So I just want to define the notion of lattice structure in a filtered infinity category. So in filtered infinity category, we have this energy filtrations, so that all geometric generator has energy 0. But I want to introduce another filtration, which I want to call script G, and so that this all operations are preserved by the second operations. And still that, you take this extension of the field from lambda 0 to lambda, for the both generators, you get the same things. So, the typical example is that in the case of most homology, then this F filtration, just to take this all critical point to have energy 0. And this G filtration, we put all geometric generator to have this energy FP. So naturally, in a most homology, you have these two filtrations, which preserves all infinite structures. And this is called, maybe we can call this doubly filtered infinity category. And so the most homology cases, most homotopic cases, suppose we have this C0 convergence of smooth functions to a continuous functions. Then we consider this sequence of this most homotopy infinity category, which has two filtrations, F0 and F and G. And this one converges to this most homotopy filtered infinity category with this lambda 0 lattice structure. So that is a more precise statement in most homotopy cases. Okay. So now I want to go back to this main constructions of this limit. So suppose we have this Cauchy sequence of gapped filtered infinity category, and I want to construct its inductive limit. So that's our main constructions, which we can reduce this to 3 theorems. So I want to explain the idea of the proofs. The first proposition is the following things. So suppose we have this two gapped filtered infinity category, and whose Gromov-Hausdorff distance is smaller than epsilon. Then we can actually construct a filtered infinity functor with energy loss C epsilon. I need to explain these notions, but first I want to say what I mean. So we have this C1, and we have this C2, and then we have this C, another filtered infinity category, so that this one are both embedded. And then what we can show is that if you just change this coefficient ring to lambda, I mean Novikov field, then this inclusion is homotopy equivalence. Because you have these two objects, so that it's a Hofa distance is finite. Then in a sense, C1 is homotopy equivalent C1 prime over lambda. That's our definitions. This is basically kind of algebraic version of the definitions. You have two Lagrangian submanifold, which are Hamiltonian isotopic. The Floer theory is independent. I mean, Floer theory over lambda is preserved. So this means that these two are homotopy equivalents. So we can cook up homotopy inverse to this inclusions. So we can just take this compositions so that we can cook up this infinity functor. And we can estimate something like how much this energy is lost by these compositions. That is this proposition. So I want to define this notion of energy loss. So the definition is the following things. Suppose we have this two filtered infinity category, and we have some the notion of infinity functor with energy loss epsilon is the following things. So we consider this bar complex of filtered infinity category. That is just you have this kind of two objects. You can just take a sequence of k plus 1 object from A to B, and you can just take this tensor product. That's basically bar complex. And then this phi kind of gives this phi k. It's kind of this bar complex to this phi1, but after taking this lambda. And this sequence of phi k gives some morphism. So this b naught is just a direct sum of bk. And this V naught has a co-product. There's something like obvious co-product. And you can extend this PK to this co-homomorphism. And you have this MK operations, which is the structures of the infinity structures, and this gives this co-derivations. And then the first condition is that this is a Cauchy map. So that is basically the condition that this infinity functor. But the next thing is that this, if you take this energy filtrations, and this energy filtration decreases. So it's not a usual infinity functor because energy filtration is not preserved, but it decreases only by this k times epsilon. So what does this mean is that this minus k epsilon go to minus infinity and go to infinity. But you fix k, this is still kind of goes to 0 as epsilon goes to 0. So this is the definition of infinity functor with energy loss. And here you see this construction of the homotopy inverse. There is an express formula, and you can see that this energy loss is epsilon. Because now we consider this inductive system of filtered infinity category and a functor. So this Vk is a filtered infinity functor with energy loss epsilon n. And suppose that the sum of the energy loss is actually finite. It means that epsilon n go to 0 very quickly. Then we can construct a limit. So this is the theorems. So this theorem basically proves this first three theorems. I mean, you have this Lagrangian Floer theory cases, then we can just take this Gromov-Hausdorff distances go to 0 in this senses, and then you can just apply these two theorems to get this inductive limit. So I want to explain how to prove this theorems. So I want to prove this thing. So we have this bar complex is like this. You have this k tensors, and then this bar complex gives something like a differential graded co-category with two filtrations. So co-category means that you have this. This is co-product, so this is the co-category, and the two filtration means that one is this energy, one is that this kind of you take this to k of this bk, and this is a kind of number of filtrations. You have this two filtrations, and then we have this phi n. This this is basically gives this map, which is a preserved co-composition and co-derivation. This is a co-functor, and it is preserved two filtrations. And one important observation is that this is linear, because you can just take this sum. So this is linear, but this infinity operation is kind of multilinear. It's non-linear. And in the case of linear functions, it is easier to take this inductive limit. So you can just take this inductive limit using this linear things. That is bare infinity. So I mean, once we take this bar constructions, we can take inductive limit because of this linearity. So we take this B infinity, and that is a graded differential co-category with two filtrations. So now we want to go back to this infinity category, just take this so-called co-bar resolutions. That is the following thing. We can just take again this tensor product. And then this guy has a co-product and co-derivations. Then it induces a derivation on this bar construction. That is very, very known things. And the product is just take this tensors. And this co-bar resolution is a filtered DG category. I just define that inductive limit to this co-bar resolution of this inductive limit of bar constructions. And you see some reference of homological algebra. If you have this DG category and you take the bar and co-bar construction, it is homotopy equivalent to the original things. This is a well-known and well established result. But the issue is that, you can just kind of allow to invert things. This is something like a limit of A, B, C of n. And then this is something like a limit Cn. So you have this natural thing. But this bar and co-bar resolution is somewhat a non-trivial thing. And then to commute it with inductive limit is highly non-trivial. Probably in this case is not correct. So that's why I just kind of very a strange way to define inductive limit. So so I want to justify these things, and so we consider this inductive limit of C. So CAB is a chain complex, and we take this inductive limit as a chain complex, and then the C infinity is just contained this A B infinity as a chain complex. And then the theorem is the following thing. So this inclusion, so you take this chain map and it induces an isomorphism of this completed cohomologies. I think this is not true if you do not complete the cohomologies. So this is the reason that justification that this is actually inductive limit. And the proof kind of based on this, on the fact. So we take this proof A, B, C equals C. And we can just mimic this proof to prove this theorems. Okay. So now I want to mention the thing. So this is basically the construction of inductive limit. But then something I want to prove is the following things. So suppose that we have this. So suppose we have this Cauchy sequence. So so we have this Cauchy sequence. I'm sorry. We have this Cauchy sequence Cn. I have this Cauchy sequence Cn prime. So then we assume that Gromov-Hausdorff distance of this two Cauchy sequence goes to 0. Then I want to prove that this sequence is something like a weak equivalent. So this shows that well-defined statement of our constructions. Suppose we have, for example, we have suppose two family of kind of perturbations of your objects, like a smooth, so you have this family of continuous functions. So you approximate it so that the C0 converges. Then I want to kind of first construct the infinity category from this and take this limit. But then you have another sequence so that it also C0 converges, but in a different way. Then we have this kind of situations. Yeah, but there's two kind of perturbations, which is a kind of which goes to 0. Then I want to prove that this limit, in this sense of inductive limit, is something like equivalent. Then for this, we need to kind of study this how this inductive limit behaves when you have these two different Cauchy sequence. And the issue is the following things. And I explained this. I explained this Gromov-Hausdorff this proposition that you have two filtered infinity category whose Gromov-Hausdorff distance is small. Then we have this filtered infinity functor with energy loss C epsilon. And I said that this is not unital. It means that the infinity functor preserves the unit. And it seems that this is not homotopic unital either. So, to define Gromov-Hausdorff distance between two infinity categories, we need unit. So it means that you have this kind of two. So you have Hofa distance. You need something like a T and T prime, and the T composed to T prime is homotopic to unit. Right? So this is a definition of Hofa distance. So kind of, if you want to prove that something is small in Hofa distance, you need to say that there are units which is compatible with these constructions. But the problem is that this construction, so you have this kind of things. You have this, this the same that's homotopic equivalent to C2. I want to construct this inverse. And the construction is kind of, to make it consistent with unit is actually difficult. So that is the reason that this is difficult to prove this weak equivalent things. But the outside the following things. So I want to define something like an infinite Hofa distance. So let me recall what was the Hofa distance. So this is the definition of Hofa distance. It means that you have two objects, A and B. Then the Hofa distance small means that you have this T, and you have this T prime, and S, and S prime. And this is the equation, right? You have this T and T prime cycle, and this difference, if you compose it, then it's a kind of homotopic to identity. And this is almost contained in this lambda 0. So that's the Hofa distance. And I want to modify this definition, so-called infinite Hofa distance. There's the following things. So in place of just two T and T prime, I have this infinite sequence of Si. So that for odd S, so this kind of things, A and B, and this Si, this is something like S odd. And even is something like this. And you have this kind of relation, which is very similar to molar Cartans. So if you take this boundary of this K, and it is something like a sum of this order product. And when K equals 2, it is 1, and other side it is 0. And this Sk is almost contained in C, and this is similar to this energy loss. Sk times c to the power k epsilon is C. So this is a definition of infinite Hofa distance. And in the case you just take this T1 and T prime is S1, and the SS prime is S2, and the required is only 1 and 2. And this is exactly the definition of Hofa distance. So this is the definition of Hofa infinity distance. And one nice thing is the following things. Suppose we have a pair, we have a Hamiltonian isotopy, and you have this Lagrangian submanifold that we move it by this Hamiltonian isotopy. There is Hofa infinity distance, just I defined, is still estimated by this Hofa distance between phi and identity. So in the geometric situations, this Hofa infinity distance is just compatible with this Hofa distance. And the same thing we can do in the most homotopy. So this is the Hofa infinity distance. And one nasty thing is that I still cannot prove this kind of triangle inequality. Actually, I have been thinking about this for a couple of days and I couldn't still prove it. But this one I found last 2 weeks ago, and I still believe one can prove it. But this equality is something like very complicated. So my algebraic ability, I cannot still prove it. But actually, fortunately, we don't need it. So we can just, this is just a conjecture. And we can just define Gromov-Hausdorff infinite distance between finite and infinity category by just using this Hofa infinite distance in place of Hofa distance. This means that you have these inclusions. So that you have any, so I have this kind of I from object of C1 to object of C2, so that the distance, Hofa infinite distance between A and IA is smaller than epsilon. So this is the definition of Gromov-Hausdorff infinite distance. And we say that the C1 is equivalent to C if this Gromov-Hausdorff infinite distance is 0. The bad thing is that, so if we can prove this kind of triangle inequality, then this equivalent is equivalence relations. But since I cannot still prove this conjecture, I don't know whether it is the equivalence relation. But still, we can prove the theorems I just mentioned. So I just go back to this proposition, that if we have this Hofa infinite distance is small, then we have finite infinity functor with energy loss C epsilon. And the important thing is that this is homotopy unital. This one I cannot prove for Hofa distance, but if you consider Hofa infinite distance, we can prove its homotopy unitarity. So now we can use these propositions. And then now we take another theorems. We have an inductive system of finite infinity category, homotopy unital finite infinity categories and functors. It means that Pn, so Pn is this Cn to Cn plus 1. And this is energy loss, epsilon n. But also this is a kind of unit, homotopy unital. So all constructions compatible with unit. Then we can construct the unit, which is homotopy unital. So the limit has unit in the case when all the morphisms are homotopy unital. Moreover, if you consider this Gromov-Hausdorff infinite distance, then the distance at infinity is estimated by this distance at the limit of the distance. So this proves that well-definedness up to homotopy, up to equivalence. But I don't like this equivalence yet because it is not equivalence relations. But you know, equivalence implies that weak equivalence, and the weak equivalence I can prove to be equivalence relations. So certainly this one is equivalence. So this gives a proof of the inductive limit, weak definedness of the inductive limit up to weak equivalence. So this is all I want to say. Thank you very much for listening.
Thank you very much. Are there any questions? Yes?
Yes. So first, I have two questions. So the first question is, have you considered a LP version of the Gromov-Hausdorff distance that you consider? Like the way that I understood it, maybe I didn't understand correctly, but you take a soup over all of the possible common spaces in which C1 and C2 can be injected on. But then have you considered taking some LP version of this?
LP, I don't understand. So this is something like a C0 version, right? Kind of L infinity version, right? So I don't know about LP versions. Yeah, because first we consider this LP norm of this continuous function. Then we go to this infinity category, right? So something like we need to first consider this LP version of Hofa norm. I mean, you have a kind of what Hofa study that you consider this space of Hamiltonian isotopy. It's something like related to this C0 norm of this Hamiltonians. And I don't know if there's an LP version of this Hofa metric. And if we can do it, we can probably do it in this case.
And the second question was, have you considered the divergence rate of the spectral dimension as lambda goes to 0?
Spectral dimension is what? Is this F lambda?
So if you go back to the slide on the spectral dimension.
Yes. Yes, you want to know how fast this lambda I converges go to infinity when lambda go to 0.
Exactly.
Yeah, I think this is very chaotic. I mean, the situation is that you take this one L and another L prime. And this kind of, AI is something like energy here. And I think you can take arbitrary fast divergent. I mean, you can take any kind of continuous functions. I mean, any C infinity functions of this area. So I don't think that there's any way to kind of have some good estimate when how fast it goes to infinity.
Okay, thank you.
You have a question? Yes. Good. So you said you didn't know about the triangle inequality for the H infinity.
Yeah.
So you can always replace D by taking the length of a path, where a path is just a discrete set of points which are at distance epsilon, and then you translate that difficulty in another difficulty, which is to figure out whether this if goes to 0 or not.
Yeah. I mean, I tried that kind of ideas for 3 or 4 days, and I still not yet successful. But probably I hope I can succeed that kind of things in a couple of months. But I don't know.
Okay.
Yeah, I mean, actually, last weekend I spent a lot of time to try to prove this some kind of triangle inequality, but I never succeed. So, but I just tried 3 or 4 days, so it might be successful some of that time.
Okay, any other question?
There is a comment on the chat.
You can see that.
How to find the commented chat?
You found it?
Yeah. So this algebraic distance is a spectral distance. I see. Yeah, I want to understand it. Yes, yeah. And also this relation to this Villain-Cornet's work is something very much natural. So it means that you have these two Lagrangian submanifold, and this Cornet and I'm sorry, SH, I cannot pronounce it. But what they do is the following things. You have these two Lagrangian submanifold, and then suppose that there is a Lagrangian cobordant. And they consider this projections of this cobordism to C. And if this area is basically this distance, and I think one can prove that this this Hofa distance between these two L and L prime is smaller than this, but than this area. In the case everything is unobstructed. That's my answer to this comment.
Which way is the inequality?
Pardon?
Which way is the inequality?
So f of Hofa is estimated by this area.
0, 8, 4, 9, 0, 9, 2, 1.
Yeah, that's. Are there any questions or comment?
Okay,
Any other question? No? Okay. So thank you very much.
Thank you.